Hello everyone, welcome to Introduction to Finite Element Analysis. Today we are going to learn approximate methods. One of the classic approximate methods used in finite element analysis is the Rayleigh Ritz method. This method involves assuming a form for the unknown displacement functions and solving the unknown parameters in the function based on principle of minimum potential energy for conservative system. This method only works for conservative systems. Based on the definition, we can divide the process of using this method into 3 steps. Step 1, we need to assume a shape or a form for the unknown displacement functions. For example, here we can assume first-order polynomial function as displacement functions. Then we introduce the 2 unknowns, a0 and a1. For the next 2 steps, we will focus on solving a0 and a1. Step 2, we need to write down the potential energy function of the system and express the potential energy in a form of a0 and a1. At the end, the potential energy should only contain 2 unknowns, a0 and a1. In order to solve them, we need to minimize the potential energy of the system by finding the first derivative of potential energy with respect to a0 and a1 and make them equal to 0. So we will have 2 equations and 2 unknowns. We can solve them easily. Now let's take a look at an example of how to use Rayleigh Ritz method to find approximate solutions. Here we have a beam subjected to axial distributed node Cx1, and we have a load P at x1 equals to L, and the beam is fixed at x1 equals to 0. So we are going to find displacement functions along x1 axis for this beam using Rayleigh Ritz methods with 0 first and second degree of polynomial functions. As we have solved this problem before using differential equation of equilibrium, now I'm going to use the exact solution here directly. After using Rayleigh Ritz method, I'm going to compare the approximate solutions to the exact solution. Now I'm going to use the Rayleigh Ritz method with 0 first and second degree of polynomial functions to solve this problem again. Let's start with 0 degree of polynomial function. u1 equals to a0. Before we do anything further, let's see if there is any boundary conditions that we can use to simplify this displacement function. We have 2 boundary conditions here. At x1 equals to 0, we have u1 equals to 0. At x1 equals to L, we have sigma 1 equals to P divided A. Let's use the first boundary condition. We can find a0 equals to 0. So 0 degree of polynomial function give us a trivial solution. Let's increase the degree of polynomial function. Let's use the first degree of polynomial function. And then we apply the boundary conditions. We can simplify displacement function. Next step, we need to find the potential energy for this beam. We have solved the potential energy for this beam before, so I'm going to use it directly. Next step, we need to express sigma 1 and epsilon 1 using displacement function. And then we plug in sigma 1, epsilon 1, and u1 into the potential energy of the system. After rewriting, we can find the final version of potential energy is a function of a1. Next step, we need to minimize the potential energy of the system by finding the first derivative of the potential energy with respect to a1 and make it equal to 0. Then we can solve A1 easily. Once we have A1, we can plug in A1 into U1 and find U1. Once we have U1, we can find sigma 1, 1. Now let's assume second degree of polynomial function as displacement function. Basically, it follows the same steps. Step 1, we assume a polynomial function. Then we introduce some unknowns, A0, A1, and A2. Then we apply boundary conditions and simplify displacement function. Next step, we write the potential energy of the system and then express the potential energy in a form of A1 and A2. Next, we minimize the potential energy of the system by finding first derivative of potential energy with respect to A1 and A2 and make them equal to 0. Now we have two equations and two unknowns. We can solve these two unknowns easily. After we have values for A1 and A2, we can plug in A1 and A2 into displacement function and find U1. And then we can find sigma 1, 1 by using equation sigma 1, 1 equals to E times epsilon 1, 1. For the third degree of polynomial functions, I'm going to leave it to you guys for practice. Basically, it follows the same steps. We assume a polynomial function, and then we write the potential energy of the system. Then we find the first derivative of potential energy with respect to unknown parameters, and then we solve for these parameters. Then we can find U1 and sigma 1, 1. Interestingly, we can find when we use the third degree of polynomial functions, the approximate solution is exactly the exact solution. When we compare the approximate solutions from Rayleigh Ritz method to the exact solutions, we can find that as degrees of polynomial functions increase, the approximate solution becomes more and more accurate, but also more and more difficult to solve by hand.